Hi students. So today we will discuss the architecture of computer. In this particular topic, we will discuss the what will be the arrangement is required of a CPU to interface with the external memory devices. So basically there are two types of architecture which are used to interface the external memory with the CPU. These two types are von Neumann and Harvard architecture. Basically, these two types or techniques are used to interface the external memory with the CPU. What will be the basic structure of address, data and control lines are required to interface the CPU with the external memory? So we will discuss one by one. So first of all, we will discuss the von Neumann architecture. So as we can see from this particular diagram, the CPU will have to be interfaced with the memory and IO devices. And again we can see that in memory, two types of memories are always required. One is called code memory. It is also known as the program memory, where we will have to store the opcodes of the program, whatsoever program we want to run, and the program is required to perform any task. So whatsoever task we want to perform, we will have to write a program, and that particular program will be stored into the memory. And CPU or processor will have to read the commands or instructions one by one from the memory and will have to execute. During the execution of the instructions or commands, whatsoever the command it will fetch from the memory, the data will have to be required. So another part of the memory which is also essential part is called the data memory. So minimum at least two types of memories are required which have to be interfaced with the CPU. And as we have already discussed during the discussion of the data structure, that minimum three types of buses are required to interface any external device, either memory or IO device. Here we can see that the CPU is interfaced with the external memory through address and data lines. Here in case of von Neumann architecture, which was proposed by the John von Neumann, and this particular architecture was used to decide what type of structure we required, what type of layout we will use, or how we will establish the interaction between the processor and memory, or how can we read the data or transfer the address to the memory. All these set of rules will be decided by this particular architecture, and it is called von Neumann. Here we can see that in case of von Neumann architecture, the CPU is interfaced with the external memory with only one set of data and address lines. So here we can see that only one set of address lines are there and another set of data lines is there. So although we will have to transfer the program and data, in any case, if we will have to transfer, or CPU will have to transfer the data and program from the memory, that particular data or opcode will be transferred through the one set of address line only. So a memory and CPU, which include the ALU, control unit, input and output devices, will be interfaced to each other through one set of address and data buses only. So in case of von Neumann architecture, only one set of address lines and one set of data lines will be used to interface the memory, either code or data. So program or opcodes or data will be transferred or received by the CPU through the same set of address and data lines. This is what von Neumann architecture is. So what are the disadvantages of this particular architecture? These are the disadvantages. It is slower in execution speed. How it is slower in execution speed? For example, let's suppose processor want to fetch the opcodes from the memory, which are the program's opcode, and it will send the address to the address lines, and those opcodes will be fetched to the data lines to the CPU. And if at the same time the previous instruction is required to read or write the data from or to the memory, the CPU cannot transfer or receive the data, because the address and data lines are already busy to fetch the opcode from the memory. That is why this type of architecture is slow. So the execution speed of this particular architecture is slow. So the second disadvantage is no parallel processing of the program. So no parallel processing of the program is possible in this particular case, because only one set of address and data lines are there. If we want to perform the parallel processing of program, so how a CPU will read the or fetch the opcodes of the two different programs, because it is having only one set of data and address lines. So it is not possible in this case to fetch the two opcodes for two different programs parallelly from the external program memory. So that is why the parallel processing of the program is not possible in this von Neumann architecture. The third one is only one information can be accessed at one time. What does it mean? The meaning of this is, for the normal process of the CPU, what processor will have to do? Processor will have to fetch the opcode from the memory, and once the opcode from the memory will be fetched to the CPU, once it will come to the CPU, and then the execution unit of the CPU will be responsible to decode and execute whatsoever the opcode is fetched from the memory. And if there is a need to read or write the data to complete that particular instruction, then CPU cannot read or write the data in parallel with fetching. So only one information can be accessed at one time. So it means either CPU can fetch the opcode at one time, or can read or write the data from the memory to complete the execution process. So these are the disadvantages of the von Neumann architecture. Next is the Harvard architecture. The Harvard architecture was introduced by the Harvard University, and this particular architecture was a slightly different architecture from the von Neumann architecture. In this particular case, the CPU was interfaced with the data memory and program memory through two different sets of address and data buses. So in this particular case, the instruction memory or program memory or code memory and data memory was separately interfaced with the different set of data and address buses, and this concept was introduced in 1947. So the concept or the methodology or the architecture in which the CPU will have the different set of address and data buses to interface the external program memory and data memory, that particular concept, that particular methodology is called the Harvard architecture. So now we will discuss some advantages of the Harvard architecture over the von Neumann architecture. So in this particular case, parallel access to data and instructions are possible. So as we can see that CPU is having the two different sets of address buses and data buses. This is a one set of address buses for program memory, and this is the data buses for the program memory. Similarly, this is the address buses for the data memory, and these are the data buses for the data memory. So parallelly, so the CPU can access the opcodes or instructions of the program in parallel with the data, because these two different sets will be used to carry one for opcode and other for the data memory. So this is the first advantage. So parallel accessing of data and instruction is possible, which was not possible in the case of von Neumann architecture. Next is the development of control unit is expensive and need more time. So as we can see that there are two different set of address and data lines are there. So that is why whatsoever the control unit we will have to develop to interface the external memory, either data or program, will be interfaced to the two different sets. So that is why it required extra circuitry, and that is why the cost of that particular extra circuitry which is required to interface the two sets of address and data buses will make it expensive, and it also needs the more time. The third is the data and instructions are assessed the same way. So this is the advantage. In this particular case, the data and instructions or opcodes can be assessed in same way as well. So both the memories can use the different cell sizes and architecture. So in this particular case, both the memories, means data memory and program memory, may be of different size, because both the memories are independently assessed by the CPU through the independent address and data buses. So in this particular case, speed of the execution will be high. So as we can see that the both program and data memory are interfaced with the CPU with the two different set of address buses and data buses, and data and opcodes can be assessed at the same time. So that is why the speed, execution speed of the processor, execution speed of the computer which is having the Harvard architecture will be high as compared to the von Neumann architecture. So naturally, if the Harvard architecture is having the two different sets of address and data buses which require the extra circuitry for the control units, naturally the interfacing diagram will become complex and its cost will be high. So this is the comparison of Harvard architecture and von Neumann architecture. So next we will discuss the microprocessor architecture in terms of instruction set architecture. In the previous topic, we have discussed that how can we decide the architecture of the microprocessor on the basis of the interfacing of the memory with the CPU. So in this particular lecture, we will try to understand the architecture of the CPU in which it will operate the capacity to perform the instruction set architecture. So in this particular lecture, we will try to understand the what type of architecture is required in terms of instruction set architecture. So from the instruction set architecture point of view, the microprocessor chips can be classified into two categories. One is called complex instruction set. It is also called CISC computers, and the another type in which the reduced instruction set computer is used. All those computers are called RISC computers. So here in this particular slide, we will try to differentiate, or we will try to compare the performance of the RISC and CISC. So this particular side is CISC, which is the complex instruction set computer, and this particular side will be the RISC, which is the reduced instruction set computer. So first is CISC. CISC instructions operate directly on the memory bank. So what does it mean? The meaning of this is, let's suppose this is the memory which is interfaced with the CPU. Let's suppose this is the execution unit of the microprocessor or CPU. Now this external memory is interfaced with the CPU. So the meaning of the first line is, in this particular case or in case of CISC, the instructions can access the data directly from the memory and manipulate it. So which means if we want to perform any operation of any location, data of any memory, that data can directly be accessed by the instruction. But on the other hand, in case of RISC processor can perform the arithmetic or logical operations only on the registers, and these are the registers. These are the internal registers of the CPU. So in case of RISC, whenever we want to perform any operation, that particular data must be available within these register only. So it means even if we will have to manipulate the data of the external memory before we want to perform the arithmetic operation, that data must be loaded from the external memory to the internal register before to perform its arithmetical or logical operations. This is the basic difference. The instructions of the CISC can access the data directly from the memory and manipulate it. But on the other hand, in case of RISC, the instructions can operate the data or manipulate the data or perform the computing operations only on the registers. So before we will start to perform any arithmetic and logical operation, we will have to load the data from the memory by using the different instructions which can be used to load the data from the external memory. So in this particular case, less RAM is required to store the CISC instructions. As we can see that the data of the external memory can directly be accessed by the instructions. So naturally, the less RAM is required to store the CISC instructions. On the other hand, in case of RISC, more RAM is required because data will have to be, or instructions can perform or manipulate the data from the internal registers only. Okay, so that is why the more RAM is required in case of RISC. More emphasis on the hardware. In this particular case, the CISC processors are the focus of the CISC processor is mainly on the hardware, and on the other hand, the RISC processors are emphasis on the software part. So the fifth difference is the microprogrammed control, and on the other hand, in case of RISC, these are the hardware control. So now, before we will try to differentiate or try to understand this difference, we will try to understand what is the microprogrammed control and hardware control. As we have already discussed that to perform any operation by the CPU from or to the external memory or I/O, some control signals will always be transferred. Some control signal will always be sent to the memory or I/O to perform any operation. So in case the microprogram control will be a type of control unit or a type of architecture in which the control signal will be generated by set of instruction, by writing the small program, by writing the micro programs. So in case of CISC processor, in case of CISC architecture, most of the control signals are generated through the micro programs which are already pre-decided and stored in the memory. So all those control signals will be generated by these micro programs. And on the other hand, in case of hardware control signal, the hardware control signals are generated by the hardware extra circuitry which will be inbuilt within the CPU, and that particular circuitry will be responsible to generate the different control signals at the different times. On the other hand, in case of CISC processor, the microprocessor or CPU will generate the control signal through the micro programs which will be pre-designed and pre-written and stored in the memory. So this is the difference, basic difference. In the next sixth one is the complex addressing mode. In case of CISC processor, the addressing modes are very complex. The complexity of the addressing mode is very high in case of CISC, and on the other hand, RISC processors are very simple, are having the very simple addressing mode. Okay, so the seventh one is the processor which is having CISC architecture require the large number of instructions. So that is why its name is complex instruction set computer. Its instruction set is complex, means it will have a large number of instructions. So many instructions are there in the CISC processor. And on the other hand, small number of instructions will be there. The number of instructions in RISC are very less, as compared to the number of instructions in case of CISC. In case of CISC, there are so many instructions. Okay, so now this next is the less work for the compiler. What is the role of the compiler? The compiler is used to compile the each and every instruction. So if a processor is having a large number of instructions, means to perform the different operations, the different instructions will be there. So naturally, the job of the compiler will be less as compared to the processor, which are having small number of instructions, means the instructions will be used to perform the more number of operation. So more work is required for the compiler. So that is why it is focusing on, or the main focus of RISC processor is the software. So that is why it is emphasis on software as compared to the CISC processor. So this is the difference between the two architecture. One is CISC, another is called RISC. So now we will try to understand with the help of one example. Let's suppose we want to multiply two numbers. Let's suppose we are having two numbers with us and both the numbers are in memory. Say this is the external memory, and we can see that these are the addresses of the memory and these are the number of bytes in the memory. So as we can see that 1, 2, 3 and 4 bytes are stored at one location number 1, and similarly another set of 4 bytes are stored at location number 2, location number 3, 4, 5 and 6 and so on. So we will assume that we are having the two numbers. The numbers are A and B and stored at some memory location, and we want to do what? We want to perform the multiplication of two numbers of A and B, and after the multiplication we want to store the result at a location which is the location of the number A. Okay, so where A and B are the memory locations. So A, the number A is stored at memory location 2 and 3. So we are assuming that the number A, which is there at memory location 2 and memory location 3. So one part of the number A is stored at memory location 2 and another part is stored at memory location 3. And for B, it is also stored at memory location 5 and memory location 2. So this is the memory location 5. One part of the number is stored at number B is stored at 5, another part is stored at number 2. So now we'll have to multiply, and again after the multiplication we will have to store the result at 2 and 3 memory location, as we'll have to store the result at A. Okay, for CISC we will write only one instruction which will be MULT, where MULT is called the mnemonic, and this particular mnemonic multiply will tells us the type of operation. So as we know that we want to perform the multiplication, so this will be a mnemonic MULT. In some processors it may be MLT, in some case it may be MUL or any other. So basically this is the mnemonic, and the role of the mnemonic is to define the type of operation. And this particular second part is called the operand, and this operand are the location of the data. So here we want to multiply the two number. One number is stored at a location 2 and 3, another number is stored at a location 2 and 5. So what this instruction will do for CISC processor, it will, again as we know that in case of CISC processor the instructions can operate directly from the memory bank. So as per the feature of the CISC processor, this particular instruction can directly fetch the data or directly load the data of memory location 2 and 3 for number A, and location 5 and 2 for number B. It will read the data of 2 and 3 for A and 5 and 2 for B, will get these numbers into the CPU and multiply it, and then again store to the this location 2 and 3. So the role of, or the meaning of this instruction is, this particular instruction is used to multiply the data of memory location 2 and 3 with another set of data 5 and 2, and after the multiplication the data will be stored to the location 2 and 3. If we look at this single instruction is used to perform the whole operation, will get the data from the memory, multiply the operand, and again will store the data to the memory. And on the other hand, in case of RISC, if we will want to perform the similar operation, if we will look at the first feature of the RISC, the first feature of the RISC is RISC instructions cannot be used to operate directly from the memory. It can operate on the registers only. So before we will perform the multiplication or product, we will have to load the data of the memory to the some registers of the CPU. So what will we do? First of all, we will load the data of 2 and 3 memory location to any register. Say A is a register, so say load is an instruction which used to load the data from the external memory to the internal register. So this load A comma 2 3 will do what? It will load the data of memory location whose address is 2 and 3 to a register A. Similarly, we will load the another data or data of B by using this instruction load B comma 5 2. So what it will do? It will load the data of memory location 5 and 2 to the internal register of the processor B. Once the data will be loaded through these two instructions, then and then only we can perform the operation multiplication. Okay, so we will write the instruction product A comma B. It may be multiplication, so this particular instruction is used to perform the multiplication. So it will do what? It will multiply the A and B, and product will be stored in A, and then again after the execution of this instruction the product will be ready within the A. So it is this particular product will be need to store to the memory location 2 and 2 3. So by writing the store 2 2 3 comma A, it will store the data of A to the 2 and 3 memory location. So if we look at difference between these two things, the difference of this particular program and this particular program, in this particular case only one instruction was required, which this particular instruction is fetching the data from the memory before the execution, before the operation multiplication. Then it will perform the multiplication within the CPU. After the multiplication, it will store the data to the memory as well. But here on the other hand, in case of RISC, in which the RISC instruction cannot be operated on directly on the memory, it can operate only on the internal register. So that is why initially data will have to be loaded for the number A, then data will have to be loaded for the number B, then perform the multiplication and then store to the external memory. So the second point is less RAM is required in case of CISC instructions, as only one instruction is required in case of CISC. So it will take less space. On the other hand, this particular CISC processor is required 4 instructions. Naturally, the memory space which is required to store the programs is 4 times more for this particular program only. Okay, so that is why it required the more space. So pipeline is easier. In this case, pipelining is harder. Look at this. If we will go with the pipeline, although we will discuss what is the pipelining in detail in the coming lectures, but for now, the meaning of the pipelining is when our processor want to perform more than one task at one time. So that is called pipelining. So if we will go with this particular instruction in which this particular single instruction is going to read the data, execution, memory read, memory write within this particular single instruction only. So the parallel processing is little bit complex, because it will have to wait the data, when the data will come, when it will start its execution. All these complexities will be come into action. Although we will discuss all these things in detail in the coming lecture, then it will be more clear to you what is the difference between the pipelining and why the pipelining is harder for CISC and why the pipelining is easier. Okay, so pipelining for RISC is easy because we can see that what is the role of load A23. It will have to load the data of 2 and 3 address only. During the execution of this particular instruction, it will only load the data. It will only read the data from the external memory. It will do what? Fetching, memory read only. This will again do what? Fetching and memory read. And this will do what? Fetching and execution. Okay, but in this particular case, it will have to do what? Fetch, read of one word, then read second word, then execution, then again write the result. So it will have to perform many operations within the single instruction. That is why this pipelining in this particular is difficult as compared to the RISC processor. Okay, so this was how can we differentiate the architecture, RISC and CISC. So we have already discussed the two topics in this lecture. One is how can we differentiate, or what type of the different methodology or methods are required to interface the external memory with the CPU, that is the von Neumann and Harvard architecture. And another was how the processor architecture can be designed for its instruction set architecture. Okay, so this was all about the architecture, RISC and CISC, and von Neumann and Harvard architecture. Thank you.